This video, we will be talking about heaps, which is essentially the implementation for the priority queue concept, which is used to support the Dijkstra's algorithm, which I assume most of you already know. So after this video, you should be able to first understand the role of the priority queue, or revisit the role of the priority queue in the Dijkstra's algorithm, and then be able to articulate the correctness of the priority queue implementation using a heap. Lastly, be able to understand the time and space complexities as usual in these heap operations. So firstly, let's revisit the concept of the priority queue and why do we need this concept in the Dijkstra's algorithm on a graph. So firstly, Dijkstra's algorithm, what is it? It is basically given a particular graph representation, like the example that we have seen previously, or a couple of examples that we have seen previously. Given any graph, starting from a particular source node, we want to find the shortest paths to each of the destination nodes, or every other node on the graph itself. We want to find the shortest path. All right, so that's basically what Dijkstra's algorithm is trying to do. Okay, so let me just change to the iPad screen. So usually we want to improve the complexity of this quadratic operation, in which indeed there is a well-established way of doing this using the concept of a priority queue, in which we can now ensure that the complexity, or the time taken to get the next best node, the node with the least cost to the particular location, is going to be log n. All right, and the update of that node can be also log n by using the concept of a priority queue. So that is the motivation behind why we are learning this topic today. Okay, so let's jump back to the other topic here. Okay, or rather the topic at hand here, which is heaps. Okay, so firstly, in terms of the terminology, okay, just wanted to be clear and contrast this with the other definition of a heap. So if you haven't come across the word heap in terms of data structures, you may have come across this term in the other popular place within computer science concepts in terms of memory. Okay, so just to be clear, we're not talking about a memory heap, and there is no real association between the memory heap name and the heap for data structures here. All right, and the heap that we are using here is basically referring to, yes, yet another kind of binary tree. Okay, and why another type of binary tree, or another specialization of binary tree, is because, as we have mentioned, it has become, or it is well known to be, the most efficient way to implement the concept of a priority queue, which serves the Dijkstra's algorithm. It serves many other different things, a priority queue, okay, but in our context of discussing graphs, it serves the Dijkstra's algorithm. Okay, so what is this heap? It basically requires us to maintain two properties. The first property is basically the structure property. The second property is the order property. All right, so the structure property simply says that it needs to be a complete binary tree. Okay, so complete binary tree means that at the leaf level, everything is packed to the left side. All right, you shouldn't have any empty space, like we have seen this before. If we had something here, then this would not be a complete binary tree, right? And for all the other levels other than the leaf, like if we look at one level before the leaf, it should be basically perfect, right? It should be perfect if we stop the tree, just before the leaf, okay, without considering the last leaf layer or leaf level. Okay, it should be a perfect tree. Similarly for any levels above it. Okay, so basically, everything should be packed to the brim. Okay, and at the leaf, so it should be packed to the left. Okay, so this way of defining is more qualitative and visual. Okay, but it's important for us to understand it this way. Of course, there are more formal math definitions which we should have already seen before. Okay, but here the qualitative understanding here allows us to appreciate that when we translate this whole heap concept or tree concept into an array, everything can be mapped 1:1. Okay, we're using some constant math formula because of how it is packed 1:1, right? So it's probably a bit hazy in terms of what I'm saying right now, and I'm jumping ahead of myself a bit. Okay, but later as we go into the examples, you will understand more why this is so. Okay, so that's a structure property which allows us to be able to pack the entire tree into a contiguous memory. Okay, and the next thing that we need to enforce, okay, is the order property, and you can think of it as like a last constrained version of the BST. Okay, remember for a BST, the node needs to be always less than the left subtree, as well as right than everything in the right subtree, or sorry, greater than everything in the right side. Okay, but for heaps, right, you just need to ensure that the particular data in your own node is less than both sides. If we're talking about mean heap, okay. If you're talking about max heap, then this should be greater than both sides, right? And I mean less than or greater than is just your own definition, right? And you can always, if you're working in C++ or C, you can always overload the operator less than, and inside you can implement it as greater than, and you will have the same result. Okay, but just saying that a heap basically maintains this property, and usually when we say min heap, means on the top of the root of the tree is the minimum value. If we say max heap, the root of the tree has the maximum value. Okay, and the order is simply that the yourself is always greater than your two children. All right, so let's look at an example of how we would translate from the structure of an array to the concept of a tree. Note that in the actual data structure implementation in code, right, this is all we will have, right? It is basically an array, but how we will treat it and work on it like a tree is that we will always remember that every operation that we do, we need to use that operation such that it treats the array structure like this manner. Okay, what I mean by that is that if you look further down in this set of notes over here, given any I, okay, you can basically apply a simple math formula to get the parent, apply another simple math formula to get the left child, and similarly the right child. Okay, and I didn't mention this, but to make the discussion in this set of notes simple, okay, we will start the array index at 1 so that the formula is a bit simpler. If you wanted to start like always, we do in computer science, start at 0, it is also fine. Okay, it's just that the math formula has a simple additional thing, like the parent needs, like this yellow color are all the ones that we starting from 0 in terms of given any I, you want to find a parent. Okay, for the yellow color, that means start from 0, you need to add another -1. Okay, similarly for this one, you just need to add another 2 times the thing plus 1, so another addition, sorry, you need to add another additional 1. And then for the right child, you just need to, instead of +1, you +2. Okay, very minor things, and probably time complexity wise, it doesn't add much meaningful time overhead. Okay, but for our discussion's sake, just to keep the formula simple, okay, we will use start from 1. Okay, just note that this is not the most important thing in our discussion here, but just to simplify things. Okay, so let's just apply this concept to one example over here. For example, if we were looking at the number 3, okay, so if I is 3, right, this means that the parent, okay, if we apply the formula of int, okay, I divided by 2, that means 3 divided by 2, this is simply equals to 1. And if we look at the index 1, which is here, okay, right? Index 1, we can see that where we were at, we wanted to see I, right? And then we got the parent as 1, which is at 10. So indeed, this is the correct parent if we were looking at it visually as a tree. Okay, and then if we continue on this, right, if we try and get the left child, okay, so the left child is equals to, which the formula is here, okay, 2 times 3 equals to 6, and 6 is here, right? 6 is here, and we can see 6, index 6 is here on the visual diagram, okay, which only we can see here when we draw it, and it's not represented in code. Okay, in code is only represented as an array. It's only when we work on it we use these math formulas, and it will allow us to work on it like the heap structure that we see over here. All right, so you can see left is correct as well, and if we just complete this and work on the right child, 2 times 3 plus 1 equals to 7. We can see that 7 is this particular location, which is here, and indeed this is the right child of I. Okay, so everything works correctly. And if you want to convince yourself and work on more examples, it's all the same. I can be 8, I can be 9, and then you can work on what the parent is, the left child, right child is. And even without working, you can even prove to yourself, just looking at the formulas, these are all, quite straightforwardly validated to be correct, right? So all this just means that, yes, in code, we can just simply use an array representation to represent our entire tree structure over here, in particular the heap structure, and in our example, a min heap structure. Okay, so this structure property is important in heaps because it allows us to do this without pointers, and that gives us a good performance boost, although it may be small in terms of time complexity wise. Okay, but everything adds up, right? Especially when this is a low level data structure, a heap, okay, that you may run millions and millions of operations over and over again on this thing. Okay, so how does this provide the most efficient? Is basically, firstly, we observe that there's no overhead in terms of pointers. Okay, so there's no extra data that needs to be stored. If I were to be using a linked list kind of a concept, right, I would to actually code this as a linked list, then I would need a pointer from this particular structure, a pointer variable, point to this, point to this. If I were to be here, the point, I need 3 pointers, okay, left, right, and the parent, because the operations actually require me to do the direction of all these 3 directions. I mean, to refer to all these 3 directions. All right, so that's no pointer overhead. And also, if we're really trying to count, the cycles to a minute extent, we can see that using the math formulas, the multiplication, the addition, and the division, all these things, right, are all faster than the dereference operator. Okay. So this is another advantage. And then this is also a huge advantage. That next one is a better locality of reference. Okay, remember that because the array representation, especially in C and C++, it is the closest to the metal. It is basically, the same as referring to the memory directly. All right. So therefore, you are allowing for, when you allocate this amount of memory, you're allocating contiguous memory, and this allows you to exploit the cache in the most probable manner, right? Okay, so that's the locality of reference, good temporal and spatial locality. And then finally, a minor thing, but basically we can get the last node in constant time as well. Okay, last node means this node. Okay, it is basically the last item of the array, so of course you can get it in constant time. If we were to implement it as a linked list kind of concept, we would sort of need like a last pointer here, which we will be able to avoid this small tiny amount of overhead over here. Okay, but just listing everything, however small it is, why we want to have this structure property that allows us to represent it as an array, simply as an array. Okay. All right. So with that, we can now move on to what are some of the operations we can do on the heap. Okay, that allows us to make it work like a the priority queue. All right. So firstly, push and insert. Let's see what it looks like, and then we'll do the usual pop or remove, and then we update. Okay, all these are, if we think about what we need to do on the Dijkstra's algorithm, all these are essential things that we need to have. Okay, essential operations on the data structure that we need to have. Okay, so the main idea for insertion, or pushing onto this particular priority queue, is to append to the end and then swim up, okay, to maintain the heap order. Okay, so these are all common terms when we are talking about acting on a heap. Okay, so we have an example heap over here, and let's just quickly glance through what the code is trying to do here. We can see that firstly, this just ensures that whether we have enough space in an array. Since we're working with arrays, we know that we need to sort of have a fixed size, and if it's not enough, we need to do that usual thing of expanding the size. Okay, and this size variable, a size of the actual allocated memory, we need to allocate more size if that's not enough. Okay, so in this case, it just tests for that. Of course, the allocate more part is not in here. We just assume that we know the maximum number of items in our particular use case. Okay, so moving on, this size variable basically keeps the last item in check, okay, so that we know how much of the space allocated for our array is being used. Okay, so when we push, we need to certainly update the size plus, and then we will next get a certain position, okay, in which we will push the item into, okay, because again, note that this is a tree with a certain structure. You cannot just anyhow put something anywhere. Okay, you need to push it in a manner that it maintains the heap properties, okay, both the structure property as well as the order property. All right, so this is what swim will help us do. Okay, we'll see what that is, and then finally, when we get the correct position, which is basically we make a hole somewhere in here, okay, we will set the value, put the value into that hole. Okay, so what is this swim? This swim is allows us to find the final location of this particular hole over here. We'll start from the last location. Okay, we'll input the final new location as the hole. In fact, it is actually a hole. Okay, let's just draw that in there. Okay, so what we are trying to do is that we will first, okay, create a hole in here, okay, and then we'll swim this hole upwards, and the hole, we know that the value that we want to put inside here is basically 18, right? Okay, so let's go through this operation. Oh, sorry, we forgot to have a brief look at what is this swimming operation. So this swimming operation, the idea is basically you bubble up this particular hole that we have created here. Okay, so while the hole greater than 1 and that the value is less than this basically gets the parent. You can see hole divided by 2. The value that we are trying to add, which is 18, is less than the parent, we will keep swimming up. All right, and swimming up simply means that the hole gets replaced by the parent, or you pull down the parent into this hole. Okay, into this hole. Okay, and then you move the hole in replacement of the parent. Okay, this is what it means, that you move up one more. Okay, divide equals to 2. That means you move up to the parent, move the hole up to the parent. Okay, let's see conceptually on the diagram what has happened conceptually, as well as actually concretely in the array structure as well. Okay, so as mentioned, we start with the hole being at the end. Okay, plus size. The starting point is at the end. Okay, and so we need to first compare whether 18 is less than whatever is in the parent. So we start from here. So this is I'll just label it as the first step. Okay, and we check whether this particular thing, okay, value is less than or equals to what is stored in the parent, which we will get by dividing by 2. So 12 divided by 2, 12 divided by 2 would give us 6. Okay, so we basically jump here. Okay, and we compare 18 whether it's less than 60. So indeed it is less than 60. So we will need to, as you can see over here, let me just zoom out a bit. Okay, we will need to put, you know, the 60 into this particular hole here and then move the hole upwards. So what this means is that I will just erase this. Okay, 60. Okay, we put it here. Okay, and then for the hole, you erase it. Well, I put dotted line so it's hard to erase. Okay, let me just do this. All right, is this particular box. Okay, so what I need to do is to, yes, I shift this hole here, which is basically, sorry to keep zooming in and out, which is basically this operation over here. Hole equals to hole divided by 2. Okay, that means my concept of a hole has moved to the parent, and whatever is stored inside the parent has been moved here. Okay, which is this particular statement that came before that. Okay, so if we look at the diagram, this is also correct, that what we actually did, right, was that we created, you know, this particular hole location over here. Okay, and then which is 12, right? You can see that all maps well. 82 was the last one. Okay, we created one at 12, which means that it's here. Okay, and then, you know, we basically pull this down here. Okay, let me just do that now. Okay, to show you know, the difference. I'll show the relation, okay, with the actual array structure. All right, and then we shifted the hole upwards over here. We shifted the purple color hole upwards, and we basically solidified this as, you know, the last item over here. Okay. All right, so now the hole is here, which also corresponds, you know, to this particular number 6 location. Let me just, yes, okay, sorry. Okay, so that's how, you know, we work on the array, okay, while maintaining the concept of a heap. So let's just continue and you know, complete this particular example over here of shifting 18. Okay, so now we're still in a while loop, right? And we move 1 upwards. We go back here and compare this thing. We are still greater than 1. This just ensures that we don't go beyond the root. Okay, we'll keep looping until this will be the final thing that we will check. Okay. All right, so this thing value, whether it's greater than, so let's maybe have a different color for the second step over here. So the second step, we are also comparing on the same value 18, whether it's less than the parent of this particular 6 location, which we can just get by dividing by 2, right? So divide by 2 is 3. Okay, so the parent is actually this 30 over here, so we compare to 30. Okay, so yes, it is still less than. So what we need to do is the same thing. We will need to pull 30 down here. Okay, we will need to pull 30 down here. Okay, and then move the hole upwards. Oops. Move the particular hole upwards again. Just draw it in red color. All right, and on the conceptual diagram, which we are using to track, you know, what it looks like in our concept of the heap. Okay, it's basically the same. We were looking at the whole, the whole being here, right? Okay, and we got the parent 30 compare, and since 30 is less than, we will, 30 is greater than 18, we will pull it down and then shift the hole upwards, right? And that will be it. And let's complete this and do the final last step. Okay, step 3 of our, you know, swimming operation. Okay, step 3 divided by 2, which is 1. Okay, take the integer, right? So 18 compare with 10. Okay, it is not less than 10. Okay, so this is not true. So if it's not true, then we already end, right? We'll swim until this is not true, right? Okay, swim until this is not true. Okay, so we don't need to move the hole any further upwards. Okay, and we can end it there, and we'll return this hole. And when we return the hole, you know, here back in our call, it is named as a position, okay, pause, and we will just replace whatever that is indexed by pause with value. So it was a hole here. Okay, in fact, I mean 30 was still 30 was still there lah. Okay, it's just that we have, you know, assigned 30 to here. Okay, so we just replace that, whatever that's inside there, not really too bothered about what is inside there. We just need to put it, the value there, which is 18. Okay, and we can see with that, let me just erase this. Okay, so 18 is here. With that, we complete the insert operation or the push operation. And we can just check that yes, it is still a heap. Okay, 10 is smaller than 20, smaller than 18, 18 is smaller than 30, smaller than 70, 30 is smaller than 60, and so on. Okay, you can check the entire left tree, which you never touch as well, but it should be correct since we never touched it, right? So this place was where we touched and, you know, disrupted the order and whatever. Okay, so we corrected stuff, and we just wanted to visually check that everything is still in place, which in fact it is. All right, of course it is, right? So we are assuming this is correct. Okay, so I'll leave you to run other examples, but I think this is enough for us to understand, you know, what the operation is. Okay, recap, you know, basically you will create a hole at the end and then try to swim this hole upwards until you reach a point where, you know, it doesn't disrupt that order, the heap order property. Okay, and then you will basically, you know, move whatever you're trying to add into the hole that you have created, okay, and shifted in place, okay, moving everything that is not in place anymore with the new addition to their new locations. Okay, so in terms of complexity, we can basically see first that this particular, so we just talked about worst case now. First, this swim operation, this particular operation over here, it is in the big O of log n, this algorithm over here, because of how, you know, this is a complete tree, all right, and it's always packed, all right, packed all the way to the left, and so, you know, this height will be log n, or proportional to log n, so therefore the maximum number of moves in the worst case is going to be, you know, proportional to log n. Okay, time time constant. I mean, if you want to be exact about the time, but we're not. We're trying to talk about big O. Okay. Yep. So that means to say that you know, this particular, okay, maybe here we need to break it up because there's a few different things. So this one will be in some log n. So maybe let's just be clear about this. So this is some constant times log n, all right? So therefore, this is some constant times log n over here. Whatever that is in front over here is a constant times some other constant. After here is some other constant, all right? All these are constant. So therefore, this entire thing will be in the big O of log n, all right? And that's what we want to have, you know, when working with the Dijkstra's algorithm, working with this the container that is in the Dijkstra's algorithm. Okay, so that is why we have it. We have the heap implementation for the container. Okay, now for pop. Okay, I have this slash remove min because the actual popping mechanism here, because of how it is trying to implement the concept of a priority tree, we are removing the minimum. Okay, so just if you want it to be exact, it is removing the minimum. But if, you know, you're just trying to create an interface of a generic container, maybe using the word pop for the method is more appropriate. Okay, so pop is just the reverse, okay, with some nuance over here in terms of how you would maintain the order and structure. All right, so the main idea of how you would pop is to return the root. Okay, because you're always trying to get the minimum thing, okay, minimum cost in terms of the Dijkstra's algorithm. It can be minimum cost of something else if you're working with a priority queue for maybe a network queue or something. Okay, so you will replace that root with the last leaf, right? The last, that's why we need the last leaf to be gotten in constant time and to be least you know, overhead as with the least amount of overhead as possible, as we have mentioned, you know, just now. If we were to screw, yep, so this is what we want. So replace with the last leaf, and then sink the leaf down, okay, because we know that we've gotten somewhere here to replace here, right? For sure, this one, we need to see whether we need to sink it down backwards in the right manner. Okay. All right. Pop. Same thing. Okay. Make sure that there's enough space. The value that you're gonna be popping. Okay, you'll just store it in there. Sorry for typo over here. Okay, just erase that. Okay, so store the value you're going to eventually return. Okay, you will minus the size obviously because you're popping, and then you will sink the thing that you will replace. Just now we were saying, right, replaced by the last element. So the last element is here, as you can see. All right, and this particular thing is, as usual, the whole, because we're starting the whole at the first item of the array. Okay, and the array starts with 1 for our simplicity's sake. Okay, so we'll sink down this particular whole index into the correct position, which is gonna be gotten from the sync operation here. And then once we have the correct position, we do the same style of thing that we will replace this thing inside the correct position with the item which is the last item on the heap. Okay, again, why am I having so many typos? Okay, I named the array as ARR underscore, okay, and not heap, right? Okay, but that's just minor. All right, then let's have a quick glance at what sync operation is. Okay, so given a whole and the value as usual, first we have some indices to store, the left child, right child, as well as the chosen child. Okay, because now we have 2 children to decide whenever we are syncing. Let's say we are here and we want to sync this particular value down to here or here. We don't know which side, right? There's 2 choices now. Just now when we were swimming upwards, there's only one parent, okay, for any node. So therefore, swimming upwards is, you just have one choice. You just go and check whether you need to swim upwards, the whole. Okay. Whereas for sinking, right, you need to, sink down, and there are two choices. So that's why we need to determine that. Okay. So yeah, just fancy terms. Okay, percolate down the whole in this particular loop over here, which, if we want to get the left child, it will be 2 times the whole. Okay, 2 times the whole here. If you wanted to get the right child, it's basically 2 times the whole plus 1. Okay, as we have established earlier, right? And this is probably quite intuitive to validate. This one is just checking whether we have reached the end, right? So firstly, in the loop, right, we store the left child, store the right child, then we do a decision making component over here that we choose the smaller child. So this is basically what it's doing. All right, this just ensures that the right child is not like over the size, because sometimes you have the an element like that and this is still maintaining the structure of a complete tree. There's no right child, and if you were to try and check the right child which is not existent, you may run into errors because this is out of the size right, and may even be out of the allocated memory location. So you don't want that to happen, and so you will check this. But essentially, the important thing is that we want to determine whether the left or right child is bigger or smaller, okay, so that we can move down into the smaller location, provided this is a mean heap. Okay, and so the chosen will be the right side if the right side is smaller, left side if left side is smaller. That's all to it. Okay, so saying the whole, and of course, one of them needs to be smaller. If they are bigger, then obviously there's no need to sync. Okay, so this just syncs the whole. All right, the chosen one, if it's less than the value, you will sync the whole. And that's the usual thing that we've seen before. And let's just look at the example. All right, so pop. Yeah, pop, no need any parameters now because you're just popping the minimum. Just erase what we drew just now. Okay, so first step is basically, okay, you set your value, okay, to be equals to the 10. Okay, it's this step. Okay, which is basically popping this root value. Okay, minus the size. Okay, so this just means that, okay, the size is now pointing to, or indexed to, this location. Originally size was here, but you shift it backwards. Okay, after shifting it backwards, and the next step that you need to do is that you would go and try and find the correct location. All right, given whatever that was inside here, array size plus 1. Okay, this thing, the thing that you want to do is, yeah, you replace it here, and you don't do that operation first lah, because you don't want to spend extra effort in, you know, setting this location to 82 and then moving it down. You basically want to find the correct location first, that means the hole. Find the correct location of the hole, then you go and set the 82 inside, so that you save the at least one line of operation there. Okay, or one step of operation, one atomic step of operation over there. Okay, so yes, which is why the next step is to find the position. Okay, and finding the position means you go and sink a particular hole, so the hole starts at 1. Okay, so the first step, hole starts here. Okay, or conceptually in the heap diagram, it starts here. All right, and then let me just zoom out so that we can see part of the code. Okay, and we will now start the loop, which we will store left and right, and then see which one is smaller. And the left is 2 times hole. Okay, the left is 2 times hole, so let's mark that out here. Sorry, my mic suddenly became further. Okay, so 2 times 1, which is 2, so left is actually here, and 2 times 1 plus 1, right, is actually here. And you know, you can actually see on the diagram this is correct as well. So we compare which one is smaller. Okay, the smaller one is obviously 20. Okay, so since 20 is smaller, we will move the hole down to 20. Okay, and let's do that both conceptually on this diagram, okay, as well as concretely in the array. Okay, so the array, we also move the hole down to 20. Okay, and that's one loop completed. All right, so there's one loop completed. Okay, we actually sink the hole. You can see this is basically what we have done. Okay, I forgot to do this particular step. We basically did this, the whole, we shifted the hole's index down, right? Okay, but we forgot to go and shift the value upwards. Remember that we shift the hole down, that means the value needs to go up. This is the reverse of just now the swimming operation. Okay, so therefore this one, the 20 needs to go in here. Let's keep this first step as purple. Okay, so concretely in the array as well, so the 20 actually replaces this. All right, that's called swimming downwards. Okay, so now let's do the second step. We choose a different color, blue color. Okay, so what we need to do in this second step, which is the second iteration of the loop. Okay, so the second iteration of the loop, we would need to, okay, first the hole is here. Let me just redraw the hole in blue color. Okay, and then we look at the left and right children. Okay, concretely we just times 2. Okay, note that again the hole is here, right? So we times 2. 2 times 2 is 4, so left becomes here. 2 times 2 plus 1 is 5, so right is here. So we compare which one is smaller. Now 40 is smaller. Okay, so left and right are here. So when we compare 50 and 40, 40 is smaller. So therefore we will move the hole down here. Okay, which conceptually this looks like that. Okay, and concretely, you know, we are basically shifting the hole down to 40, and when we shift the hole down to 40, before that we need to shift 40 upwards. Okay, so shift 40 upwards into the original location. Okay, so 40 would now be here. Okay, I say shift lah, okay, but there's no real need to actually delete anything from here. Okay, we just set whatever in the data that's stored inside here to this location. Okay, not to waste any cycles doing extra things. Okay, but I'm drawing this, erasing this just to show what we have done. Okay. All right. So next, starting the third iteration of the while loop, our whole starts at this location over here. Okay, this location over here. So what we need to do now is that similarly we get the left and the right child. Okay, so left child 5 times 2, which is 10. So it's here. The right child, we actually cannot get the right child because note that again, you know, the size we set to here, this is actually the right, the last item already. Okay, so if 2 times whole, okay, less than or equals to size, which is still fine, we can still get the left child, but this particular thing, the right child is not less than or equal size because the right child is supposed to be here, right? 2 times 5 plus 1, 11, but the size is at 10. Okay, so remember that just now we actually imaginarily you know basically shifted this to here, or rather we want to, you know, replace that and sync down, right? So that's what we were trying to do. Okay, so actually there's no item here, and 82 is really the item that we want to insert back in the correct position. Okay, just explaining what's happening here. Okay, but basically, yes, if we follow the algorithm, right, the right child cannot happen. Okay, so therefore the chosen one can only be the right child. Sorry, left child. The chosen one can only be the left child, which is this condition over here because this is violated. All right, and so we will do the same, you know, syncing down of the whole. Okay, so we can only sync down the whole if it is less than 85, but since the thing that we're comparing with 82, okay, 82 is not less than 85, so actually we don't even do this. Okay, note that the array in the chosen thing, okay, which is 85, okay, array in the chosen child 85, it's not less than 82, which is the value that we want to move into the right position. So this is not done, and therefore we will basically stop here and return the whole, and the final whole is at this particular location. All right, and final step, okay, final step here is to actually set it to 82, and so final step will be, let's put it in red, 82. Okay, and that will be done, and obviously this one doesn't exist conceptually already because our size points to here. Right, and that's how you know you will pop something, right? And that allows us to fix, you know, the tree after we pop. Okay, summary. So pop means that yes, we go and basically extract the root, okay, because the root will be the minimum value if this was a min heap, okay, or minimum cost if we put it in the context of Dijkstra's algorithm, right? And when we remove this thing, obviously something needs to replace it, and the way how we replace it is to get the last item, okay, get the last item here, okay, and then try to move it into the right place. The conceptual idea is that you replace it with the last item, just now was 82, and then you move 82 down to the right position. That's the conceptual thing, okay? But programmatically, you know, we basically create a hole, move the hole into the right place, and then put the 82 inside there. Okay, so that's a summary of what we have done over here. All right, the time complexity will be fast because, I mean, it's the same thing, all right? Because of how we are moving, you know, up and down the height of the tree, and height of the tree is log n, right? So the rest of the stuff are basically constant, and I don't think I need to go into any, you know, complicated analysis here. We can basically, I believe, okay, fairly easily establish, you know, that the big O is in log n. Okay. Now, let's move on to something else, which is updating of the priority value for each for any item over here. Okay, so just to recap that, you know, in a Dijkstra's algorithm, every time, you know, there is a certain cost value inside there that would allow for it to be chosen. Sorry. Okay, so just to recap, in, for example, Dijkstra's algorithm, there's always a certain cost value that is being maintained in any of the node. Okay, and the cost value can change because of how we are updating, the shortest path to this particular node over here. So the cost will change, and once we change the cost, inside the tree where this is residing, okay, which the nodes are residing to be determine what order to process, right? We need to update where it resides in the heap, okay, where it resides in the heap. Okay, so once we go and update this particular value, we sort of need to determine whether it needs to move somewhere else because of how the value has changed, and it will disrupt the heap property. Okay, so that's basically what this update priority is doing. And if we roughly look at it, firstly, the main idea is that given, any pointer to a value, we will change its key. Okay, and when we change its key, we will sink and swim to maintain the heap order. Okay, note that we need to give it a reference to the location, which we have if we relook at the Dijkstra's algorithm. Okay, because we want to avoid in a heap to find a certain particular value. That takes time. So okay, so with that out of the way, I think we look at the details of what is being done over here. Basically, given reference to or pointer to a particular value inside the heap, a particular node for that matter, the priority to update, okay, we will do this. Okay, firstly, we will set at the old priority to the current, whatever is in there, the existing priority. Okay, so if we were to draw this here, maybe if this was the current priority for, let's just draw it in terms of a normal heap structure. Okay, so let's say the current priority is 3, all right, and then the new priority is probably what we want to update is to update this to something else, maybe 5. Okay, then we will need to do these steps. Okay, firstly you store the old priority as a 3. Okay, and then we set it to the new priority, which is what we have done over here, to 5. If the priority is less than the old priority, okay, so basically what we are checking here is if the new priority 5 is less than the old priority 3, which is not true. Okay, so we will do this. Okay, sorry, we will check this other thing. Okay, if it is greater than, okay, so in fact it is greater than, this is greater than, okay, then we will sync it. So note that yes, when we upgrade this, right, we can just put in the other values previously as well. So maybe for example 4 and 6. Okay, this is actually a correct heap structure, right? Maybe the root is 1. Okay, so after we update, you can see that when we put an update of, for example, 5, this already disrupt the heap property because 5 is greater than 4. Okay, 5 is greater than 4. So therefore, we need to shift this. And the only way to shift this, since this is greater than, is to sync it. And these conditions are basically testing for which case is it. Okay, just imagine that if we change this value, let's say 5 now becomes 2. Okay, if we update the priority to something smaller, okay, we change to 2. Okay, and so 2 now becomes less than 3. And if it's less than 3, the original value, then what we need to do is to basically swim. Okay, potentially swim, sorry. Okay, So we will check whether we need to swim, because you lower this value, then maybe it's lower than the other value on top. Okay, so the example here, okay, maybe a better example is this. Okay, let me just change this example. Okay, let's say originally, okay, the parent of 3 was 2. And then, our change was this. Our change update of the priorities that we update to 1. Okay, and so 1 is now is a value that is less than the original value 3. So we need to check if we need to swim upwards. Indeed, we need to swim upwards because sorry, let me just repeat this. Yep, indeed we need to swim upwards because 1 is actually less than 2. Okay, but this will be settled in the swim algorithm. Okay, in the swim function. All right, so that's what this is trying to do. Okay, and I also don't so that that already establishes how the correctness of this algorithm happens. Okay, so let's not delve in much further than that. But if you have any questions, certainly you can still ask me, okay, in the comments. And I think also, the fact that once again, whether we are swimming, keep doing the erasing, whether we are swimming or whether we are sinking, it goes, through the height of the heap, okay, which we have established that is proportional to log n. So therefore, the complexity, the time complexity is going to be in log n. All right, so all these things are all in log n, all these operations on the heap. Okay, which is what makes it nice for things like Dijkstra's and other places where you need a priority queue concept to happen. Okay, lastly, given that we have so far assumed that we already have a heap, what if we don't have a heap and we have a random number of things that we have stored in a container? Let's say we stored in an array. Okay, we want to convert that into a heap. Given any container of things, okay, we need to first fix the structure. Okay, that means make it into a heap structure. Okay, if we were given an array, it's already done. Okay, if it's an array, then it is already done. All right, contiguous array, obviously, without any missing in between values. All right. Then then the other thing that we need to do, which is the hard work here, is to fix the heap order property. All right. And there are 2 ways to do it. Starting with the naive method, okay, without thinking deeper any further. Naturally, what we can do is to go and push everything using the heap push property, right? Yeah, to be exact, this is like heap push. Okay, given any array. So this would naturally need to be in some order of log n, right? And I mean, sorry. And so this complexity would therefore be, you're going through all the items in the array, obviously, okay? And times this particular push operation, which we know is log n. So this heapification is actually n log n, right? And actually, you can do something a bit more cleverer without affecting this. So it's still going to be n log n, but that it's going to be half the time practically. All right, and again, we want to save all the time possible, even if it's not, in big O terms, right? In the abstract high level complexity analysis terms, still, we can, using this, okay, make sure that the time is actually, whatever, if this was, if this, was actually built from a time complexity of some constant, okay, of n log n, then we can basically have the same c n log n divided by 2, okay, the constant sorry, the whole time complexity can divide by 2. Obviously, this is still the same, you know, n log n when we talk about n log n terms, okay? But just saying that practically, you know, this may have some benefits depending on your use case. All right, and the thing that we are doing here is simply this, okay? Start from size divide by 2 and sink down. All right, so instead of pushing one by one into you know, the heap, okay, we will sink down from halfway point onwards. Okay, we can see that this actually works, okay, because all these values, right, are at the leaf, so there's no need to like sink anything beyond the halfway point. All right, because sinking does almost nothing, right? There's nothing here to sink. And we know that sinking every element, okay, so the intuition is you sink every element, for sure, you know, you will get a heap, right? Because you go through every element and sink basically ensures that whatever they're trying to sink down would be in the right position, all right? Or the right position of a heap order. Okay, if you go through every single node and you sink down, then obviously it's gonna work, right? So the thing is that there's no need to sink this level because all of them are already sunken to the bottommost leaf level. All right. Okay, so if we follow the algorithm, well, we start from size divided by 2, which in this case would be 7. So we start from I equals to 7, which is here, okay? And then we sink it down, which previously we have already seen. So I will just skip all the details. You know, we find that between the two children, left and right, this is the smaller one. So we'll sink to the right side, which simply means that at the end of the operation, this 4 will be here, 13 will be here, and then we will minus I, okay, minus I. Now I equals to 6, which is here. If we were to, in the previous operation, if we were to go and do the sinking on the actual concrete array as well, we will see that this is what is going to happen. Okay, now at this particular 6 location, know that we are minusing, okay, and always sinking the element that we are at, okay. So similarly, 12, 1, 1 is the smaller one, so we will do this operation of sinking 15 down to 1's location. All right, so 15 and 1, if we update the actual array, 15, 1, sorry, oops. Okay, my eraser is too big. Okay, 1, 15, and then we continue maybe one more. Okay, so minus I equals to 5, I equals to 5 is here, and so there's nothing for us to do because 5 is less than both its children already. There's nothing to sink. Okay, so maybe we just continue a bit more. I equals to 4 here, right? I equals to 4. Similarly, 3 is already less than 9 and 4, so there's nothing to do here. Then we continue minus I equals to 3. I equals to 3 here, and we can see that yeah, we need to sink this. Okay, so firstly, 1 and 4, 1 is a smaller one, so we will sink 8 down to 1. Okay, 1, 8. Okay, let me just reflect that in here as well. 1, 8, and then one more time. Okay, sink is not done yet, we need to go all the way down. Okay, 8, 12, 15. Okay, this is already in order, so there's nothing much to do. All right, and maybe let's just complete this entire thing. Okay, so the next item to be processed, okay, is minus from 3, which is 2. Okay, so 2 is here, and we can see the 2 is already in order. Okay, good. Okay, 3 and 5 are both bigger than 2. There's nothing to do. And finally, we reach the last one, okay, which is I equals to 1. Okay, one more color here. Okay, I equals to 1. Okay, I equals to 1 here. And we have something to do because 10, if we look at 2 and 1, it's both smaller than, and the smaller one is 1, so let's move there. Okay, sink there. 1, 10, we reflect in our concrete array, 10, 1, which is in fact where we will be really working on. We are just working on the array, and we don't have the conceptual representation. This is just for understanding sake. Okay, and then at 10 is still greater than both sides, and the smaller side is 4. So therefore we will sink down to 4 there. Okay, so 4, 10 in the actual thing is going to be like looking like this. 4, 10, and then okay, one more step, 10, 6, 13. Okay, 6 is still less than, and the smaller child, so we will need to shift, we will need to sink one more level down. Okay, 6, 10, right? The actual thing we are operating on, the array. Okay, 6, 10, and finally we are done. Okay, so we can check everything. Is it a heap, or rather now is it a heap? After we done this build heap operation, we can see yes. Okay, 1 less than both sides. All right, 2 less than both sides, 3 less than both sides, 5, and we can check everything, and it's really a heap. So we can see that to build a heap, there's no need to go through every single node in there. Okay, we just need to start from the halfway point, which really is the level before the leaf. Okay, we just process, you know, from here onwards, okay, all the way backwards, go and sync every one of them, and then we will get a heap in the end. Okay, so this is a more efficient version of building a heap rather than the more naive version. But if we look at it a bit more carefully, we can actually see that the improvement in terms of complexity is even higher, actually. So just now we had the more high level intuitive version of, you know, the improvements that we will get, even without what I will quickly show in terms of the more rigorous method to establish a more tighter bound, okay, in which the tighter bound is actually this particular build heap operation is in the order of ON, okay, which is even much better than ON log n. Okay, but just saying that even without tighter bound, okay, we can already see intuitively that the improvement over the naive version is quite a lot, okay, in terms of it being halved. All right. So let's look at what this more specific analysis is, which allows us to get the tighter bound of big O of n, all right, linear time. Okay, it's a bit complex in terms of the math over here, so I will not delve into the details, okay, but just give the intuition of how we arrive there as usual. So if we look at what we are doing over here, right, so really written down, you know, at each level, what are the abstract number of iterative operations that we are doing. Okay, like when we are swimming, right, we just now note that, yeah, we started from here. Okay, if we just look at, yes, this one, that we have 4 nodes. Sorry about that. Okay, we have 1 node, 2 node, 3 node, 4 node, okay, which is the 4 number here. Okay, times, in the worst case, we will compare 2 times, right? Because we go down 1 level here, and then including the ending while loop, you know, the worst case, the operation, or rather the statement that we will do if we go, yeah, the statement that we will do in the worst case, this case, in the last time we will still do that 1 more time. So in the worst case, we have 2 comparisons, okay, in that statement. Okay, so this is the 2 times. Okay, in this level, okay, all these nodes would have 2 times of the iterations of the worst statement in the while loop. Okay, and then if we go 1 level upwards, okay, we have 2 things that we need to swim down, okay, and in each swimming operation we will at the most do, you know, 3 iterations of that while loop, okay, in the worst statement. Okay, similarly at the root, okay, we have just 1 node that does, you know, in the worst case 4 times. Okay, here you look at this last level, we know that we did not do this in the actual real algorithm, the time we saved from not having to do that swimming. Okay, but just including this as well, if we were to do the swimming operation for this last level, you know, there would be 8 of these nodes that will do this. We include this is more for simplicity of the proof that we will see down here, okay? So that it's easier to see the proof, all right, and nothing much more else. Okay, and here we can see that we're just translating everything here in terms of this is 1 times of basically and divide by 2 to the power of 1. Okay, here this is the next level, 2 times of n, and as usual, the total number of nodes. Okay, divide by 2 to the power of 2. Again, if we write it in this fashion, and if we just rearrange things, sorry for that, if we just rearrange things such that it looks like something that we can apply using a standard formula, and in which case standard formula is this geometric sum over here. Okay, and we know that yes, there are several assumptions over here just to make all the formulas work well for the purposes of this proof over here. And the end, if you look at what is being done over here, which I will not delve into the details, okay, we would be able to eventually establish that this is in the big O of linear time complexity. All right, so just importantly, note that yes, the improvements are not trivial, okay, from n log n to n. All right. And so there's this last section on Heapsort, okay, which we can just extend the idea of having this particular heap structure that allows us to always get a minimum item, and if we just keep getting the minimum item and putting it back into the array, it would allow us to actually get a sorted array. All right, so I'll leave you to look at this as one of the other options of sorting something. All right, with that, that's all. See you guys next time.